Hi, it's time for another math easy solution. Time to discuss further into polar coordinates and now look at example 4, which looks at the circle or writing a circle using polar coordinates. And in this example, I'm going to graph it, but before I get to that, I just want to go over a brief overview of graphing with polar equations. So the graph of a polar equation r equals to f of theta. In other words, if we have r as just a function of theta, and it's usually written like that. If you have, this is the polar axis, and then let's say you have, actually this one, yeah, we just remove that x for now. Just so what we have is, if we have r like this, we have a point there, and this is r. So as you extend r, the theta is the same if you have r is greater than 0. So it doesn't matter if what you change r, the theta is going to be the same. But if you change theta, then r changes. So r is a function of theta. But you could also have, for example, if r is like this, if you go backwards, that's when you have r is less than 0. Then what happens is the thetas change. So this theta would end up being something like this instead. So in this more general case, this one here, for this case you have r as a function of theta, but now you could also have this one as theta is a function of r as well. So theta equals to r, actually better than that, I'll write f of r, for example. So theta is also a function of r, because if you change theta to here, you get a different version of r. And as well in this case here, because r is dependent on theta, you have as well r as a function of theta, like that. So basically what we end up having is, in more general, we could just do this instead, so that we just have a function of r and theta that just equals 0. So if we just take this, it's for both cases, if it's negative or positive, you have r equals to function of theta. So let's combine this and move this over. You have r minus, like this, r minus f of theta equals to, well, 0. So now this is just a giant function of r and theta equals to 0. So this is more general and accounts for everything. Yeah, whether r is negative, theta is negative, etc. Just dealing with all that. So this basically consists of all points P that have at least one polar representation r theta whose coordinates satisfy the equation, this one here. So if this is P and this is coordinates r theta. So if it has at least one like that, and that's what we have. Yeah, and basically all the points that are that satisfy this equation are part of that polar curve. So now let's look at the example. Yeah, so let's look at this example, which says what curve is represented by the polar equation r equals 2. So remember, r is just a function of theta, and in our case, yeah, we have this equaling to 2. So this means that r is equal to 2 for all values of theta. So because of that, and we know that r is a distance, yeah, and we know that since r represents a distance from the point to the pole, because remember, this point P all the way to the pole or origin O, like that, then basically the curve r equals 2 represents the circle with center O and radius 2, because as you change this theta, all we're doing is getting a circle. So for example, if we have this like this, I'm just going to draw this x for the polar coordinate or the polar axis. So what we have, if we have a point here, so let's say this point here and this distance is r equals to 2, like that. So we have theta, but as you rotate theta, the distance always remains 2. So what we end up having is a circle. Let's draw this better, like that. So yeah, what we have is a circle. I'll just fix it up. It still doesn't look like a circle. This is a circle. And now if we want to go even more general, well, what we could do is just write r equals to a, where this just represents a circle with center O and radius, well, absolute value of a, like that. So for any value or any constant like that, I'll move this down so we could draw some additional curves. So let's draw this one in red. So let's say we had it smaller. So what we could do is let's draw this in red like that. This is at r equals to 1, for example. If you want to go even smaller, this could be something like r equals to 1/2. And bigger than this, we can go all the way across. And let's say this is r equals to 3. So as you change it, you're going to have a different circle like that. And yeah, just fix this up a bit. Yeah, so the circles don't look that good, but you get the idea. Just a function r equals to a constant is a circle. And yeah, I just want to go over a quick note. Yeah, this example shows, well, the usefulness of polar coordinates in defining circular curves or equations as compared with Cartesian equations. A circle with a center at the origin is going to be, well, x squared plus y squared equals to r squared. And if you were to graph it, you just get a circle like this, where the r is just the radius. So we have something like this is y, x, like that. So then if you draw this across like this, at this point, this is the radius r, this is the y, that's x. And just using Pythagoras' theorem, you get this point at x, y, and that just equals to x squared plus y squared equals to r squared. And you could even just use Pythagoras' theorem as well. So Pythagorean theorem to understand that as well. Yeah, but on the other hand, Cartesian coordinates are better suited at graphing straight line segments. For example, let's say if you were graphing y equals to 2, that's just a straight horizontal line. This is the x, this is the y equals 2. So that is our y equals to 2. If this point here is 2, like that, this is 1, 2, etc. And likewise, you could also graph vertical ones like this. If this line right here is, let's say that's x equals to 3, for example, this is 3, 2, 1, etc. Yeah, so just a constant is just a straight line, but a constant equation like this for polar coordinates is a circle. So yeah, that's how you could kind of understand the different coordinate systems. Cartesian is more just the xy perpendicular linear type of coordinate system, and polar is the circular one. In later videos, I'll see how to graph straight lines using it. It's pretty interesting. Anyways, that's all for today. Hopefully you'll learn from this interesting video, an interesting example on using polar coordinates to graph the circle and compare it with the regular Cartesian coordinates. Anyways, that's all for today. Like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.